Hey friends, welcome to my channel and in this video I am going to discuss about a very important topic for any competitive exam, and this is the Felkin-anh model and the Cramps rule to predict the stereoselective outcome of a reaction on chiral ketone or aldehyde. So for that we have to first understand what are the preferred conformations for chiral aldehyde or ketone. And you can see I took this model compound, this model chiral aldehyde for our example. You can compare this with this real compound. So generally when you have a chiral compound, the carbon atom next to the carbonyl group is the chiral carbon, and that's why it will have three different groups, and that three groups you can classify as large, medium and small. And in this case you can see the similarity between two is that in this case the phenyl group is the largest atom, then methyl is the medium, and hydrogen is the small. So accordingly this compound we can write like this. Now the best way or the easiest way to do a reaction or to observe a reaction, we have to draw this compound in the Newman projection formula, and the Newman projection formula of this compound will give you this. So here you will have hydrogen. Now here you have the largest atom, so I represent it by L. This can be phenyl, and these two are your methyl, and this is your hydrogen. Now you can do a RS nomenclature for this compound. For example, we take this as A, then this large as B, this medium as C, and the small as D. So it will give you A, B, C. You can see this is anti-clockwise, and a small group is from distant to you, and that's why this will give you S configuration. Same is true for this. Now while you converting this flying wedge structure to this Newman projection, this RS relationship should be maintained. And in this case you can see I can do the nomenclature like this. This is your A, this is B, and this is C. So here again you can see this is a anti-clockwise rotation. That's why we have written down the right form of the structure. Now this is one of the conformation, but we can rotate one of the bond to get different conformations possible. And in this case we have to rotate by 60 degrees so that we cannot get any eclipsed conformation. We want only the staggered conformation. Now if we first rotate by 60 degree, the conformation we will get like this. So here you have hydrogen, and I am rotating in this direction, so your methyl group will go here, and your, so actually it is not methyl, it is medium group. So medium group will go here, and large group will come here. Now hydrogen will come here. This, then you can again rotate by 60 degree, and that will give you a structure like here you have hydrogen. Now your medium group comes here. This is actually small group. Okay, this is actually the small group. This is hydrogen, same. So this is now your small group, and this is your large group. Then you can further rotate this. So if you rotate further, what you will get? You will get your hydrogen here. Now you can see the small group will go here, and your large group. So actually this is your large group, and this is your medium group. Okay, so after that you can again rotate the structure, and you will get, so if you rotate another 60 degree, what you will get? You will get this hydrogen here, and now you can see the your large group will go here, your medium group will come here, and your small group will go here. Okay, so you can see if you further rotate this structure, you will get the same thing. So this is 1, 2, 3, 4, 5. So another rotation is possible. So if you rotate another round, you will get this structure. Here you will have hydrogen, and now you will have the large group here, and this medium group here, and the small group here. So if you rotate another 60 degree, you will get this structure. So these 6 conformations are possible for this compound. Now in this case, one thing you should notice that all these 6 conformations are not the stable conformation. only two are the most contributing structure, and what are these two you have to determine like this. So this largest group, in this case the largest group is this L group, so that conformation which places this large group away from this hydrogen and this oxygen, that will give you the more stable conformation. So in this case this is one stable conformation, and another stable conformation is this one. Okay, so we have to pick these two. So these two will determine the outcome of our reaction. So we can erase the other conformation, because you can see in other conformations the large group is either either closer to this hydrogen or closer to this oxygen, but we want a conformation where the large group is away from this two group. So basically these two are now our major contributing structure in the assembly of all the conformations. Now we have to see the attack of a nucleophile when the nucleophile is attacking on the carbonyl group. So for this we have to know the Barghi-Dunitz angle, that is whenever you do a reaction on the carbonyl compound, you know that the nucleophile come in a particular angle, and this is called the Barghi-Dunitz angle. The angle is like this. So attack from both phases are possible, but it has to come like this. This is a specific angle 107 degree. So in this case we can see what are the possible attacks. So here you can see for this conformation we write it as A and this as B. So in this A conformation the two possible attacks are like this and this. So here you have the nucleophile and here you have the nucleophile, and in this case you can see the attacks are like this and this. So these are the nucleophiles. Now for this particular conformation, you can see when the nucleophile is attacking on this carbonyl group, it has to be proximate to this, either to this large group or to this medium group, because the position of this attack is such that the nucleophile has to come within 30 degree angle of this large group for this side attack, and within 30 degree angle while attacking from this side. So both of these attack are not favorable, but in this case you can see, although when the nucleophile is attacking from this side, it has to counter attack a steric hindrance from this large group, but when it is attacking from this left side, there is no such possibility of interaction, because here it has to face only the small group, and small group means hydrogen. So hydrogen, there is hydrogen means there is no group, so there is no such steric interaction. So this is the most possible attack or most favorable attack, and that's why between these two populated conformations, this is the reactive one, because although these two are populated almost equally, so we can draw a equilibrium sign like this. Population of them are more or less same, either it may be 45 55 or 50-50, but this is the reactive conformation. So whatever conformation are stable, that all are not reactive. Reactive conformations are such that which face the less amount of steric interaction and more amount of orbital interaction. So in this case you can see this is the conformation which face the less amount of steric interaction. So whenever you have to predict any stereochemical outcome of your chiral carbonyl compound, chiral ketone or aldehyde, you have to draw these two conformation, and selectively you have to react on this particular conformation. Now if the nucleophile attack on this carbonyl center, what product you will get? So you can get this product. You can see the medium group is there, and the small group is there. So here you have the large group. Now what you will get? You will be getting this one. So here you have this nucleophile, and here you have this oxygen, and here you have this hydrogen. So this is the compound. So in this case it may be OH. So this is the product you will get. Now you can convert this structure to your flying wedge structure. For example, if I convert this structure into flying wedge structure, I have to just look at the bond in this case involved. So you can see the backward bond, I can write the medium group on the top, and there are another two groups. So if I place the medium group top, you can see the large group is coming toward me, and the small group is behind the board. On the other end, in this case you can see I can place the hydrogen here, and these two groups are now, you can see this hydrogen, if here this OH group will come towards me and this Nu group will go behind the plane. So this is the structure which of the product which we will get. Now I will show you a real example. This is a model compound, but I will show you a real example of application of the Felkin-anh model. So in this case, you can see again these two conformations are the most populating structure. Now let's say we react with this compound with lithium aluminium hydride. So reduction of this compound. Now you can see in this case these two, both of these attacks are not favorable because they have to face this either this methyl group or this phenyl group. But in this case you can see when the attack is taking place from this side, it has to face the hydrogen atom. So this is the favored pathway of attack, and out of this you will get this compound. So here you will have ethyl group, you have this hydrogen and this phenyl. Now you have this oxygen OH, and here you have the phenyl, and here you have the hydrogen. So when you convert this structure into your flying wedge or your Shawhorse structure, what you will get? You will get this ethyl group here, this phenyl group here, this hydrogen here, and in this case you have this phenyl group here, okay, and this OH group here, and this hydrogen here. So this just need a few practice. After doing a few practice, you can do it very easily. So this is example. Now we will discuss example when you have electronegative substituent in your compound. So for example, let's say this is our compound. Now we will just draw the more stable conformation. So let's say you have a phenyl group here, and you have so you have a compound where you have a SPH group here, and you have a ethyl group here, and you have this hydrogen here. So now this molecule can have another conformation like this. So if you just rotate the bond, what you will get? So you can rotate it like this way. Then you will have the ethyl group here, the hydrogen here, and the SPH group here. Okay, so these two conformations are possible. Now while you are predicting the reaction outcome, so let's say you are reacting this compound with lithium borohydride. Okay, so if the reaction takes place through this conformation, because we already told that you have to place the largest group away from this phenyl and the oxygen. So in this case the largest group is this ethyl group, because it is a branch, or instead of ethyl group you can have a isopropyl group. So let's say it is isopropyl group, then the comparison is more easier, because you can see this is compared to this SPH group, this isopropyl group is bulkier. So what I have told till now, this is the most reactive structure. So if the reaction goes through this most reactive structure, the hydride will attack here, and you should get this your as your product. Okay, so SPH, and here you will have this hydrogen. Here you have another hydrogen which is actually attacking, and here you have this OH, and here this pH. Now indeed for the reaction, when you do the reaction with lithium borohydride, but in this case it is observed that the product what you will get, the reaction takes place from this particular conformation, and you get this product instead. Okay, so you get this product. Here you will have this isopropyl group, and here this hydrogen. So this is in contrast with what I have told till now, because in this case this is the most reactive conformation, but I have told that you have to place the large group away from this oxygen and phenyl, but in this case you can see the large group is placed close to the oxygen. So why this is happening? So in this case, one thing you have to note is that whenever you have electronegative substituent, instead irrespective of its size, it should be always placed perpendicular to the carbonyl group. So you can see in this case the SPH group is perpendicular to this carbonyl group, but in this case it is not perpendicular to this carbonyl group. So why this is the case? There are two factors. One is electronic factor, Coulombic repulsion between these two groups. You can see it as lone pair. So if you place this like this, then there will be a Coulombic repulsion. So that's why it will try to stay as much away from oxygen as possible. So that's why it will go perpendicular to this. And another reason is the increment of the reactivity of that compound, and that is some other reason. I will discuss some other video. But you should note that whenever you have this SPH group, it should be always placed perpendicular to this carbonyl group. And if you place perpendicular to this carbonyl group, then this becomes the most reactive conformation, and it will give you this product. Now the outcome of this reaction totally differ when you react this do this reaction with zinc borohydride. So for example, when you react the same compound with zinc borohydride, then instead of getting this product, you get this product. So now why the difference is there? So this is the effect of chelation. Okay, so in this case what happens, the zinc ion have a very good power of chelation. So what it do is that the zinc go here and it coordinate with this oxygen and this sulfur. So now due to this chelation, this particular conformation becomes most stable as well as most reactive, because the chelation increases the electrophilicity of this carbonyl center by coordinating with this oxygen. Okay, so that's why this is now become the most reactive structure. And while placing this electronegative substituent on perpendicular to this group give you the more stable and more reactive structure. For normal case, when you have a coordinating ion, the reaction will go through this chelation and you will always get this as your product. So this is the effect of chelation, and there are few groups and few ions which are susceptible to this chelation. For example, instead of SPH, if you have a OMe group or any OR group, that will also be susceptible to this chelation. So any group that has lone pair and can do this chelation with this metal ion, that will show this chelation effect. And all the ions, metal ions, will not show chelation effect. For example, when you have cation as your sodium plus or potassium plus, they will not show chelation effect. But in some cases lithium can show chelation effect. Although in this case you can see when we use lithium borohydride, it is not showing chelation effect, but in some instances the lithium can show chelation effect. But your magnesium 2 plus, then manganese 2 plus, then zinc 2 plus, cerium 3 plus, these ions will show the chelation effect for sure, because their chelation power is very much high than this ion. So when the reaction is occurring in presence of this type of ions, you have to be careful that the reaction will follow the chelation effect pathway. So this is one important factor, and I will show the last example of chelation, because you can see in this case the chelation is basically occurring through a 5-membered ring system. Okay, so in this case zinc ion was there. So in this case you can see 1, 2, 3, 4, 5. So 5-membered ring is forming. But in some cases the chelation reaction can go through a 6-membered transition state also, and that one example I will now discuss. So this is the example where you have phosphine compound, and in this case if you do the reaction in just sodium borohydride, then the reaction will follow this pathway, that is this is the then the reactive conformation, because in this case you can see the electronegative atom is placed perpendicular to this group, because there is no such coordinating group. In this case the cation is sodium, so it is not at all coordinating, and in this case the reaction will take place from this side. So hydride will attack from here and you will get this product. So here you will have R dash, here you will have OH, and here you have hydrogen. This is your R, this is your H, and this is your phosphine group. Okay, but when you do the same reaction in sodium borohydride, you are doing the reaction, but you are adding cerium 3 plus ion in this case. So when you add the cerium 3 plus, the chelation will occur and the reaction will follow different pathways. So in this case you can see the chelate ring is here 1, 2, 3, 4, 5, 6. So in this case it is a 6-membered chelate ring, and the reaction now will happen from this side. So you will get this as your product. So here you will have OH, here you will have R dash, here you have R, and here you have PO, PH2. You will have hydrogen here. This is your hydrogen. So this is a very important example, and I almost discussed all the important examples for Felkin-anh model. So there is another model called not model, another rule. This is called Cramps Rule, and that also give the same in most of the cases the right answer, but that rule is based on some observations of a collection of reactions, and that doesn't have any theoretical background, and that rule is actually it has some fundamental problems. It gives the right answer but for wrong reasons, so you shouldn't follow that rule. The Felkin-anh model is enough to predict this type of reactions, and I hope this video will help you a lot. If you like this video, then subscribe my channel and share this video with your friends and give thumbs up. Thank you for watching.